Hello, we are Buckeye Vertical from The Ohio State University.
This year, our drone, the Airbrutus 1, is a hexacopter 8 feet in diameter, made of 2 composite fuselage plates, carbon fiber tubes, and is supported by a carbon fiber truss system. Our propulsion system uses the Titan Air TA8010 motor coupled with a 30x10 carbon fiber propeller and is powered by 4 10,000 mAh batteries connected in parallel. The vehicle can hold up to 5 payloads on its bottom fuselage plate, and to drop them utilizes a spring-based parachute deployment system. For the season, the team chose the Pixhawk 4 for the flight controller, running the PX4 software. To receive video feed, Airbrutus 1 has a CE ZR10 camera connected to the NVIDIA Jetson Nano to process the live video feed.
The SUAS competition rules and Buckeye Vertical's mission plan lay out several vehicle requirements for Airbrutus 1. Airbrutus 1 must be able to fly for both 12 miles and 50 minutes fully loaded in a single flight, with the additional ability to fly 10 miles in 15 minutes. Airbrutus 1 must then be able to complete the payload mission in 10 minutes to leave a 5-minute safety buffer. To satisfy these requirements, the aircraft's gross weight must be less than 40 pounds. Additional requirements include a 90% image detection accuracy, 150-foot object detection radius, and 25-foot maximum waypoint error. The airdrop zone is a 15-foot radius circle around the ODLC object. To ensure the airdrop lands within the circle, the team requires Airbrutus 1 to be able to position horizontally within 1 foot of the object. Additionally, the payload must land within 4 feet of the aircraft's position. To comply with the competition's weight rules and optimize speed and flight time, the team created a 1.5-pound acceptance requirement for each payload. These criteria combine to satisfy the main requirement of aircraft stability. Lastly, the team requires a maximum 10 feet per second impact velocity for the payload, ensuring a gentle landing.
The main airframe of Airbrutus 1 is composed of 2 1/4-inch balsa wood fiberglass plates. The balsa wood was laser cut into the desired shape from the CAD, and the fiberglass was added to the balsa wood using a wet layup process. The drone's arms are made of circular 1/16-inch thick, 36-inch long carbon fiber tubes, which were cut using a circular saw. Metal brackets were used to fasten the tubes to the fuselage plates, and between the 2 fuselage plates exists a Delrin hex connection system, which connects all 6 carbon fiber tubes to each other to minimize vibration and provide rigidity to the frame. Outside the fuselage plates, a carbon fiber truss system is used to connect the ends of the arms of the drone. These tubes are 1 32nd-inch thick and connected using a 3D printed bracket. The purpose of the truss system is to minimize oscillations at the end of the drone's arms. The propulsion system of the aircraft consists of 6 Titan Air TA8010 motors alongside 30x10-inch props with an iFlight Blitz 80A ESC. 4 of these motors are canted to 2-degree angles opposite of each other. This canted configuration allows the aircraft to have more yaw authority without affecting the roll and pitch of the aircraft. These motors are mounted to the carbon fiber tubes using vibration dampening mounts. The drone is powered by 4 6-cell 10,000 mAh batteries connected in parallel for a total of 40,000 mAh. 4 landing gears were 3D printed and mounted to the fuselage plates, sharing a bracket with the carbon fiber tubes to reduce weight. The RTK was mounted on the top plate to ensure signal was received, and the Jetson and Pixhawk were mounted near this RTK to ensure they could communicate with each other. The batteries were mounted on the bottom plate to ensure a low center of mass for stability during flight. One of the alternatives considered for the drone was a VTOL fixed-wing design where 2 of the rotors would rotate 90 degrees. The design was abandoned due to complexity of the flight and the weight of the aircraft. Additionally, Garolite 10 plates were considered for the airframe, however they were not sturdy enough and were prone to vibrations.
Our UAS uses a CCR10 camera connected to an NVIDIA Jetson for processing the video feed. The video is processed by the NVIDIA Jetson using YOLO V5 on its onboard GPU to identify the shapes, colors, numbers, and mannequins. After the location is obtained from the detection model, this data is then processed and transmitted to the Pixhawk to perform a specified translation in its environment to drop the payload.
We considered other cameras such as the Canon M50, but the CE-ZR10 camera was the best choice due to its high-quality 10x optical zoom as well as its built-in gimbal. Furthermore, the camera of choice is compact and lightweight, which is perfect for the specified objective.
The payload system operates by servo-activating the freefall of a water bottle capsule, which is slowed close to the ground through a drone-attached parachute. The system consists of 3 major components: capsule, release, and deployment. The capsule secures an individual bottle and enables easy setup for varying shapes and sizes. It also contains a parachute holder, and one end of the deployment line. Using PLA and carbon fiber materials ensures the weight requirement is met. For the release mechanism, 2 PLA supports hold the capsule against the fuselage bottom. A servo rotates one support, which releases the capsule. The deployment mechanism is responsible for opening the parachute 20 feet above ground, which optimizes drop time by using free fall for 75% of the sequence. The 60-foot deployment line connects the parachute to a tension lever on the fuselage bottom. The lever causes parachute deployment, then immediately drops the line from the aircraft. This system satisfies time, weight, accuracy, and safety requirements. 2 system alternatives were considered: standard parachute descent system and winch descent system. Testing of the first alternative, which used immediate parachute deployment, resulted in only 10% accuracy. Despite being the lightest system, it was rejected in favor of highly accurate systems. Winch descent was not tested, but instead estimated to be considerably heavier and slower than the selected system. Because of their comparable accuracies, it was rejected.
With the multicopter being inherently unstable, we will use a PX-4 in conjunction with a PIXOC to address flight stability. Alternatives such as ArduPilot were discussed, however simplicity and compatibility with the onboard Jetson favored the PX-4. On the ground, Q ground control is used with the 915 MHz telemetry module to transmit vital parameters of the drone. Q ground control is used to plan missions according to the competition rule, and different mission parameters are set for optimal path and speed for endurance and completion time. Safety was enforced throughout the season. There were 2 main areas where safety was implemented: manufacturing and flight testing. During manufacturing, a lot of procedures were done by hand, so safety was essential. Members would utilize gloves, safety glasses, and masks whenever those parts of the body were at risk of harm. For example, while doing wet layups of fiberglass on balsa wood, members would be careful to utilize gloves and plastic tools to ensure epoxy resin didn't stick to the skin. Another example is while drilling holes on the fuselage, members would ensure gloves, safety glasses, and masks were worn.
For flight testing, safety was always a priority. For the transportation of the UAV, batteries were always stored inside a bat safe, accounting for the worst possible scenario. Once at the destination, the drone was not powered onto the shunt plug until the drone was checked for faults and was fully built except for the propellers. The drone's motors were then individually tested before removing the shunt plug and installing the propellers. Once the drone was ready to fly, there was a dedicated team member to make sure the drone was not armed so that other team members could move the drone at least 50 feet away from the team. After a flight was completed, a member was assigned to immediately remove the shunt plug from the drone while standing outside the prop arc.
In order to maintain the safety of our drone, we follow a strict 3-stage process before deploying our software. This is a demonstration of our first stage, simulation. Here, we are using JMavSim to test our use of Mavlink commands to autonomously control the drone off board. In this demo, the drone takes off and then travels to 2 different XY positions. With the use of this go-to-point logic, we are able to dynamically adjust our pathing based on our input from our payload target localization algorithm. The Mavlink commands are the communication sent between the NVIDIA Jetson running the algorithm and the PIXOC interfacing with the drone hardware.
One of the most essential processes to get the drone flying properly is the tuning process. A major component of this process is tuning the PID controller. Buckeye Vertical aimed to use the inbuilt PX4 auto-tune command to do so. To get Airbrutus 1 to be stable enough to successfully execute this command, the team utilized the PX4 flight review website and performed analysis on the PID plots that were generated. The team used the Ziegler-Nichols method to tune the PID parameters based on the PID plots. However, despite the team's valiant efforts, the drone was unable to be tuned in the yaw axis due to weather restrictions, time constraints, and inexperience. This was unfortunately the biggest obstacle in the team competing in person this season. Although the final result may not be what the team desired, the team truly learned a great deal from this very valuable experience.
We decided that the most efficient method of training a model for the large number of possible payload target combinations was to create a large data set using domain randomization. With domain randomization, we're able to simulate every single possibility in the target, as well as every single possibility in the environment around the target. With such a diverse data set, we're able to train the model to adapt to the real-world situations that it might encounter. When we tested this model on real-world data, we consistently reached above 90% confidence rates.
Buckeye Vertical had a great season, but unfortunately, due to time constraints and unforeseen circumstances, we're unable to meet all the flight readiness requirements. With that being said, Buckeye Vertical has gained a tremendous amount of knowledge with all the hard work that was put in this season. The team plans on completing the drone regardless of not competing and looks forward to sharing a video at that time. Buckeye Vertical thanks you for this opportunity and looks forward to competing in person next season.